Good morning. So we are starting with lecture number 6 in electric drives course. In the last class, we had looked at load equalization, where if we are going to have a huge variation in the load, so for example, a bottling plant or a cutting machine, where we are going to have a high load torque for a short while and very light load torque for a long duration, again a high load torque. So whenever a bottling plant, a bottle is being closed with the help of a cork or something, at that point you are going to see that a high load torque comes into picture. Other than that, you are going to see continuously the motor is rotating, but with very light load torque. So this is the time versus the load torque variation. This is how it is going to be. Now, if there is a huge variation in the load torque, rather than really depicting this large variation in the load torque directly to the motor, if we are able to kind of put some kind of energy storing mechanism in between, something like a flywheel. So it can store some amount of kinetic energy whenever the load torque demand is lower, and it can release that energy whenever the load torque demand is higher. So in that case, you may just see that the electromagnetic torque developed by the motor could be somewhat like this. It could actually very well be much lower than whatever is the TL max that is being demanded by the load system. So this will also reduce the complete rating that we are employing for this particular drive system. That will also reduce the cost of the motor that I'm employing in this particular drive system. So load equalization is to make the load kind of evened out or leveling the load when it is being depicted to the motor. That's what we are looking at. Okay. So this particular mechanism definitely can be used in a system where the speed is only in one direction. So the one of the conditions is the speed or the rotation has to be unidirectional. If it is bidirectional, it has to reverse every now and then. It is going to be really difficult, or it is impossible for you to use this flywheel, because we all know this equation J d omega by dt is equal to TE minus TL. So if I'm going to have a higher value of J, then the time that is taken for reversal or the speed variation is also going to be very large. So if I put a flywheel in a mechanism like an elevator or a hoist, you cannot really expect the response to be faster because the overall inertia is going to increase tremendously. So unless a mechanism is having unidirectional speed demand, only in that case a flywheel can be used. Another major thing is, like there is torque variation. We said that the variation in the torque of the motor itself is going to be from TE max to TE minimum. So this is how the the electromagnetic torque is going to vary. At the same time, we said again, if you look at the speed is going to vary like this. It is going to come down during this, and then it is going to increase and again come down, increase, and so on. So this is going to be the mechanical speed variation. So if your system cannot tolerate mechanical speed variation, so mechanical speed variation is bound to happen. Mechanical speed variation is bound to happen. So it should be able to withstand any variation in the speed. If it cannot withstand variation in the speed, then you cannot be using this kind of flywheel mechanism. Please understand that the flywheel is going to store energy in the form of half J omega square. So obviously, if it is releasing energy, omega m will decrease. If it is gaining energy, omega m will increase. So you are going to see continuously whenever it is releasing energy, you are going to see that the speed decreases, otherwise the speed is increasing. This is what we drew as the speed variation. So speed variation is bound to happen in the case of a flywheel being used for load variation. It will happen definitely. Okay. Now that we have understood about load equalization, let me try to work out one problem on numerical problem on load equalization. So let me work out this problem so that the concept becomes somewhat clearer. So let me try to, first of all, the problem statement goes as follows. It is the motor, what we are considering here is a 6-pole, 50 hertz, 3-phase, wound rotor, induction motor. Has a flywheel coupled to its shaft. The total moment of inertia of the flywheel plus motor plus load. So the total moment of inertia J of the flywheel plus motor plus load is equal to 1000 kg meter square. Okay. So another thing that is given is the maximum load torque demanded by the load. T max demanded by the load is 1000 Newton meter for a duration of 10 seconds. So this is TH according to whatever derivation we did in the last class. The light load period is long enough to allow the motor to reach its no load speed. So we are also assuming that the light load is equivalent to 0 Newton meter. There is hardly any torque required during that duration. The slip of the motor, the rated slip of the motor is 3% at TR, that is rated torque of 500 Newton meter. Calculate 1. What is the maximum electromagnetic torque developed by the motor. Second is what is the speed at which the shaft rotates at the end of TH, that is high load period. Okay, so let us now try to see how to solve this problem. So let's first of all write the data clearly. One is the no load speed, assuming that the slip is negligibly small. So the no load speed of the system is going to be, this is an induction motor. So the no load speed, if the slip is 0, we are going to have this as omega s. That is if the slip is 0 at no load condition. So I should be able to write this as, this is 6-pole 50 Hertz motor. So 120 F divided by P, which is 120 multiplied by 50 divided by 6. So this is going to be 1000 RPM, which I can write as 104.7 radians per second. Okay, so no load speed is this. And what is given is the rated slip of the motor is 3% at the rated torque of 500 Newton meter. So TR is 500 Newton meter and omega R, that is the rotor speed at 500 Newton meter torque being developed by the motor, that is going to be 1 minus 0.03 multiplied by 1000 RPM. Right? So that is 1 minus S times omega S. So that will be 0.97 multiplied by 1000 RPM. So that will be 970 RPM. So if I try to draw the speed torque characteristics of the motor, I should say this is the speed and this is going to be the torque. And at 1000 RPM, I'm going to have 0 torque developed and at 970 RPM. So if I say this is 970 RPM, so at 970 RPM, we are going to develop, or the motor is going to develop 500 Newton meter. So this is TR and this is omega R and this is omega S, which is same as the no load speed. So we should be able to substitute this in the expression what we require when we calculate the moment of inertia of the flywheel. But here the moment of inertia is given. So J is given as 1000 Newton meter. TL max is given as, rather J is given as 1000 kg meter square, sorry. And TL max is given as 1000 Newton meter. TL minimum is given as 0 Newton meter. And TH, the time duration for which the high load torque is encountered by the motor, that is going to be 10 seconds. But TL is really not given because it says that the motor is on no load. It is long enough to allow the motor to reach its no load speed. So that means if it reaches a steady speed, J d omega by dt equal to TE minus TL. That's what we write. So if a steady speed is reached, that means d omega by dt is going to be 0. So this d omega by dt becomes 0 means TE should be equal to TL, which is equal to 0 Newton meter during light load period, especially at the end of light load period. It is going to be literally 0 Newton meter. That's what it is saying. Okay. TE should be equal to TL and both of them are at no load condition. So it is going to be 0 Newton. Okay. So now that we have all these values, let us try to take a look at what we looked at in terms of the derivation we did in the last class. So here is the derivation what we did in the last class. So we said that j omega naught minus omega r divided by tau r equal to TL divided by natural logarithm of this particular expression. This is corresponding to light load period. But if you are talking about high load period, which is TH, let me write this clearly in this particular, the new page that I have opened. So let me write this. This is going to be tau m equal to TH divided by natural logarithm of TL max minus TE minimum divided by TL max minus TE maximum. Okay. And this tau m is given by the expression J multiplied by omega no load minus omega rated divided by T rated. This is tau m expression. Okay. Now we calculated already 1000 RPM corresponds to 104 radians per second. So 970 RPM corresponds to 970 multiplied by 2 pi divided by 60. So that is omega r and that corresponds to 101.53 radians per second. So let's try to substitute these things here. J is given as 1000 kg meter square. Omega no load, that is 1000 RPM, which is 104.7 radians per second. And omega r is 970 RPM and that corresponds to 101.53 radians per second. That divided by TR, which is actually 500 Newton meter. Okay, so this is going to be our tau m. And this tau m comes out to be 6.34 seconds. Okay, so the time constant has the dimension of exactly time. That's why we have written 6.34 seconds. Now TH is given by 10 seconds. And this is natural logarithm of TL max is 1000 Newton meter and TE minimum in all probability will be 0. That's what we said here. At the end of light load period, both TE and TL, both are going to be 0 Newton meter. So this I can write as minus 0 divided by TL max is again 1000. I have to solve for TE max. I don't know what TE max is. Okay. This is equal to 6.34 seconds. Okay, so I should be able to write this as 10 divided by 6.34 equal to ln of 1000 divided by 1000 minus TE max. Okay. So I should be able to write this 10 by 3, 6.34 is 1.577. So I should be able to write this as e power 1.577 is equal to 1000 divided by 1000 minus TE max, from which we are able to solve for TE max. Now TE max comes out to be corresponding to this expression. TE max comes out to be 793.4 Newton meter. So TE max is 793.4 Newton meter, although TL max is equal to 1000 Newton meter. So we should be able to employ a motor whose overall torque developing capability is less than this 1000 Newton meter. So naturally we will be able to save on the cost of the motor. Now we already wrote that omega, that is omega no load minus omega rated divided by TR, right? That is the slope with which our speed torque characteristics of the motor that is actually governed by this particular straight line. So this is TE and this is going to be omega and this is no load speed and this is the rated speed and this is going to be the rated torque. So when a torque of 793.4 Newton meter is developed, what is the speed? If we calculate, that is going to be the speed at the end of the high load interval. Please let us try to look at what kind of, the speed variation the drive is having. So at the end of the high load period, it is having a reduction in the speed. At the end of light load period, it is having an increase in the speed. So the speed is increasing during light load period. The speed is decreasing during high load period. So let us try to take a look at what is the speed at the end of high load period. So this is omega no load minus omega r divided by TR. This is the slope of the speed torque characteristics. This multiplied by TV max will give me how much is the reduction in the speed. So omega no load minus this will give me what is omega mechanical at the end of TH interval. So this is going to be equal to, I can say omega no load is 1000 RPM. And let me write it in terms of radians per second itself. So I'm going to write this as 104.7 radians per second minus 104.7 radians per second. And 970 RPM corresponds to 101.53. So I can say 101.53 divided by 500 Newton meter multiplied by, this slope has to be multiplied by 793.4 Newton meter. So this entire thing comes within a bracket and that has to be subtracted from 104.7 Newton radians per second. So this comes out to be 952.4 RPM. So at the end of the high load period, the speed reached by the motor is 952.4 RPM. So the total variation in the speed is from 1000 RPM to 952.4 RPM. This is going to be the total variation in the speed. Okay. And similarly, the load torque is going to change from the electromagnetic torque is going to change from 793.4 Newton meter to 0 Newton meter repeatedly. This is what it is going to do. So with a flywheel of 1000 kg meter square inertia, we should be able to limit the speed variation from 1000 RPM to 952.4 RPM. And the electromagnetic torque variation is changing from 793.4 Newton meter maximum until 0 Newton meter minimum. Okay. So this is the effect of using a flywheel. Okay. So today we are going to switch over to another topic within the general aspects of drive system, which is known as control and sensing in electric drives. So we are going to mainly look at what are all the different types of control loops that we use in an electric drive system. So first of all, let us try to understand a drive is going to operate mainly under three different conditions. One is steady state operation at a particular speed and a particular torque. Steady state operation at a particular speed and while delivering a particular torque. So this is the first thing. The second thing is maybe acceleration. Whenever I want to increase the speed of the drive from a particular value to another value very quickly. So acceleration. So this is again a transient operation. Similarly, retardation or deceleration. So these two are transient operating conditions. So if I take, for example, an induction motor drive or a separately excited DC motor drive, we are going to have the characteristics somewhat like this. In the normal operating condition, these are the kinds of characteristics we are going to have for a separately excited DC motor drive or an induction, three-phase induction motor drive. So this is omega axis, and this is going to be the torque axis. Okay. So if this is the kind of condition we are having, and let us say I am having a specific load torque demand, which is a constant load torque demand. So this is what is my TL. I might like to operate my drive at a particular speed, which is corresponding to this particular speed. So I may like to operate it at a particular speed, which is omega 1. Or I might like to operate it at some other speed which is corresponding to omega 2. So for a given load torque, I may be able to operate it at a particular omega 1 or particular omega 2. So I have to ensure that my motor follows this characteristics or my motor follows this particular characteristics. So this, whatever I have shown in black color is the speed torque characteristics of the motor. Okay, so if I try to follow, or if my motor follows this particular speed torque characteristics, then I'm going to have the operating point as A. This is going to be the operating point. Rather than that, if my motor is following this particular speed torque characteristics, then I'm going to have an operating point B. So the crux of the matter is I should be able to adjust the operating condition of the motor corresponding to operating point A or corresponding to operating point B. So my control of the motor drive, the control loop should act in such a way that either it operates in point A, operating point A corresponding to speed omega 1, or it operates in operating point B, which is corresponding to the speed omega 2. So I should be able to achieve a specific speed or a required speed by setting my requirement properly in my control loop. So the control loop generally could be a speed control loop, or it could be a torque control loop, or it could be a position control loop, because I might like to adjust the position of a particular lens or particular tool or something like that, lens in a telescope or microscope, or I might like to have my tool adjusted in a particular way in a CNC, computer numerically controlled machine. So CNC machine, I might like to adjust my tool at a particular position. So I might like to have position control loop or speed control loop or torque control loop. Now, during transient operating condition, for example, I might like to adjust my motoring operation or regenerative operation as per the requirement. So, for example, if let us say currently I am operating my electric vehicle or something at a particular speed and at a particular torque. So this is going to be my torque requirement, and this is going to be the speed requirement. So this is essentially TR, and this is going to be omega R, and this is the omega axis, and this is the torque axis. Now, let us say I want to bring my electric vehicle to rest condition. So I want to bring it to rest condition, which corresponds to omega equal to 0. This is going to be omega equal to 0. Okay. So if I want to bring it to rest condition, abruptly I cannot switch from this characteristics of the motor to the last characteristics, which is corresponding to this. So if I want to bring it completely to rest, I might have to do it on a step-by-step basis. So let me draw again another characteristics for the motor, the third characteristics for the motor. So let me call this as characteristics number 1. This is characteristics number 2. These are going to be the characteristics corresponding to number 3, and this is 4. So what you might try to do is, currently we are operating at this particular speed. If suddenly I'm going to reduce the voltage or something from C1 to C2. So maybe this corresponds to some particular voltage V1. And I'm going to change this to another characteristics which is corresponding to V2. Now, when the voltage is changed, the motor characteristics will change from C1 to C2 abruptly, but the speed cannot change abruptly. So currently, the motor is operating at this point. So what will happen is, now because the speed cannot change abruptly, now this is the speed, omega R is the speed. So the operating point is slowly shifting from A to B. So it has shifted to B. At operating point B in characteristic C2, the torque developed is 0. The torque developed is going to be 0. So at operating point A, TE is going to be TR and omega is going to be equal to omega R. But when the voltage is changed from V1 to V2, the characteristics followed by the motor becomes C2. So now because it is C2, the speed is still omega R. But in C2, the torque developed is equal to 0 because omega R corresponds to now the torque developed by the motor. So this is operating point B. This corresponds to operating point B. Okay. Now, at this juncture, if I try to write what is J d omega by dt, that is going to be equal to TE minus TL. TE is 0 and TL is TR because it's a constant load torque. So this is the constant load torque characteristics. Whatever I have drawn here is the constant load torque characteristics. So this is going to be the constant load torque characteristics. So the load torque is a straight line like this. So this is going to be TR. Now this is TR. So obviously I'm going to have d omega by dt becoming negative, which is equal to minus TR divided by J. That is what is going to be d omega by dt. So the motor is going to decelerate. As it decelerates and it reaches this particular value of speed, that is going to exactly match with the load demand. So you will not see any more deceleration, but you want to bring the motor to rest. So what you would do is to reduce the voltage to V3. Now again at V3, if I try to look at it, maybe I will have the speed somewhat like this. If I call this as operating point C, corresponding to operating point C, the speed is something like this. So this particular speed is, let us say, omega R dash. So at omega R dash, I'm going to have in C3 a negative torque developed. So from C, the operating point shifts to D. So this is the way the operating point shifts to D. So from A, it has shifted to B. B is exactly at zero torque condition. And from B, it is slowly shifting to C. And at C, the torque is going to be equal to TR. And now at C, you are shifting the voltage to V3, which is less than V2. So you are going to see that from C, abruptly the operating point shift to D, where the torque developed is negative and the speed is still omega R dash. Now, because of the torque being developed is negative, J d omega by dt equal to TE minus TL, which is corresponding to a negative torque, negative TE. So this is going to be maybe minus TE1. And you are going to have TL is TR. So this is a large negative value. So that is going to essentially allow the motor to decelerate really fast. So it is decelerating really fast. Then after that, you might try to reduce the voltage to V4. And under that condition, it is going to decelerate even faster and reach literally zero speed. So during control of the transient operation of the drive, the machine has to continuously get a signal that the drive system has to continuously get a signal that the voltage has to be decreased further and further. Initially, it was at V1. Now it has decreased to V2 to reach the operating point B and then C eventually. Now further the voltage is decreased to V3 so that from C it goes to operating point D, and from D it is going to reach the operating point E. Then further the voltage is decreased to V4 so that the operating point ultimately reaches F, where the zero speed is reached. So the control operation of the electric drive has to ensure that the control variable like voltage or current or something like that, that is decreased further and further. So basically, during transient operation, the drive system goes from first quadrant of operation, which is motoring, to the second quadrant of operation, which is actually going to be regeneration. So regenerative braking is repeatedly implemented to bring down the speed. And in the process of bringing down the speed, you normally see that you are developing a negative torque or zero torque. That is the reason why we call the second quadrant of operation, which is actually here, the second quadrant of operation, which is actually here as regeneration or regenerative braking. Because here the torque is negative, whereas speed is positive. This is what we talked about in our second lecture, I suppose, regarding a four quadrant operation, which is forward motoring and forward regeneration, then reverse motoring and reverse regeneration. So this is repeatedly used whenever we want to reduce the speed or increase the speed, acceleration and retardation. When we want to do, we have to ensure that the appropriate value of torque is developed. During acceleration, you have to probably develop a very huge torque because you are going to have again J d omega by dt, which is d omega by dt has to be positive. So J d omega by dt also has to be positive. That will be added to the load torque ultimately to develop a huge electromagnetic torque from the motor side so that acceleration takes place properly at required rate. Okay, so the control loop has to ensure that appropriate value of voltage or current are really applied to the motor so that sufficient value of acceleration or sufficient value of retardation is ensured so that the motor ultimately reaches a steady operating point. And the steady operating point, what is reached, has to be again the reference speed what we require. So if we want really 1000 RPM, then 1000 RPM has to be attained. So the control loop has to ensure two things. One is accuracy of speed and torque. And the second one is response time. The response time should not be too large. The drive system has to respond within certain duration properly, within the required duration accurate. That is very important. Okay, so if we want a particular value of speed to be attained, so this is the reference speed. So we have to compare that with the actual speed. So the actual speed is obtained by a speed sensing mechanism. How are we going to sense the speed? That we are going to look at now within some time. So this is speed sensing mechanism. The actual speed is compared with the reference speed. Now what we get is the speed error. Now, the difference in the speed between the reference value and the actual value, that is speed error. Now, this speed error has to be nullified eventually. So, there will be a speed controller which will be sitting in between. The speed controller could be a PI speed controller, fuzzy logic controller, ANN based controller, PID controller, whatever is the control mechanism that we are employing here. Now the speed controller has to ensure, because I have J d omega by dt equal to TE minus TL. So if I try to develop a larger amount of electromagnetic torque, then I will have a particular d omega by dt. So within a particular duration, this particular error in speed, the gap can be bridged. The error can be bridged. So you will ultimately reach the required speed. So the speed controller invariably will say so much of torque needs to be developed so that the error in the speed can be bridged, or the gap in the speed can be bridged. So the torque is going to be the stimulus which will actually bridge the gap in the speed. Okay. So for developing the torque, I will have to probably push a particular amount of voltage or push a particular amount of current. So invariably, the torque is developed by pushing a particular value of current. So this has to be translated into a current value. Or I can say I can have a torque to current converter. Most of the times the torque is going to be proportional to the current. And if I try to look at it, this will be K phi I in most of the cases. So I should be able to calculate the current right away if I know what is the kind of torque requirement the drive has to bridge the gap in the speed. So now I have the torque to current converter. So what I get out of this will be a reference current value. Now this reference current will be compared with the actual current. So I will have from here a current sensing mechanism. So I definitely need to study about the current sensing mechanism as well. That's what I'm trying to get at. Okay. Now the output of this is going to be current error. Let me call that as delta I, whatever is the current error. Now this current error will be nullified by having a current controller which may increase the duty ratio in the case of a chopper, or which may reduce the rheostat position to certain position where the resistance will be smaller, or I'll be able to, adjust the firing angle or something like that. So this will give me a control signal. So this control signal will go to the power processor. So this power processor now is feeding the motor. And motor, of course, is coupled to the load. Now, between the motor and load, whatever is the coupling, from there, I will have to sense the speed. So I can say this is going to be sensed. The speed is going to be sensed from here. So this is speed, which is being passed on to the speed sensing mechanism, which ultimately reaches, the control loop here. So this is going to be the reference speed and this is the actual speed. The same way, I have to have the current sensing mechanism. So between the power processing module and the motor, whatever is the connection, I can actually put a current sensor right here. So this is going to be the current sensing mechanism, which senses the current from this current sense. So this is going to be a current sense. So this is a typical control loop that I'm going to have for a motor drive, where I want to achieve a particular value of speed. That particular value of speed is compared with the actual speed that is being sensed. And the difference between these two, that is actually communicated as the speed error to a speed controller. The speed controller could be an analog controller, a digital controller, a software that is written within the computer. Maybe it is a PI or fuzzy logic controller. Now, this speed error is processed by the speed controller. The speed controller is going to say, if I have so much of torque developed by the motor, then the speed error can be bridged within a particular duration dt. So that is going to decide how much is the electromagnetic torque that has to be developed. Now, definitely this has to take into account two things. What is the d omega by dt I require, and what is the kind of load torque requirement that is being posed by the load. Both of them together will decide what is the electromagnetic torque. Now, this electromagnetic torque is normally proportional to the current. So that will be converted into appropriate current value, which becomes the reference current. And that is compared with the actual current that is received from the current sensor. Now, that error in the current, this is the current error, what I have got, that will be passed through a current controller. We will again look at different types of current control mechanisms also, like PWM current controller and hysteresis current controller and so on. And this current controller will be passed on to a control unit. So this is the control unit which develops the control signal, which is passed on to the power processing unit. So this is the control unit, which might vary the duty ratio or firing angle, or it is going to probably change the modulation index or frequency for an inverter. All those things are being done by the control unit, and that control signal is given to the power processing unit. The power processing unit is going to increase or decrease the voltage or current or the frequency. One of them is going to be modified, and that is passed on to the motor. Now, between the power processing unit and the motor, there will be a current sensor sitting. This could be a current sensor, voltage sensor, depending upon how the torque is getting adjusted, and that is actually passing on the actual current value to the current controller ultimately, or comparator and current controller. So this is the overall configuration of the control loop for the motor drive when I want to control the speed. One thing I want to emphasize is the current control loop is the inner loop, whereas the speed control loop is the outer loop. So let me reiterate, speed control loop is going to be the outer loop, whereas current control loop is going to be the inner loop. Speed control loop is generally governed by the equation J d omega by dt equal to Te minus TL, where moment of inertia plays a very, very vital role. Whereas current control loop is going to be governed by L di by dt equal to maybe V minus Ri. So this is going to be governed by the electrical equation, whereas the speed control loop is going to be governed by the mechanical equation. So here the time constant involved is tau, which is in all probability L by R. So this is electrical time constant, which really governs the time duration which is taken for controlling the current. So electrical time constant is generally of the order of only a few milliseconds. Whereas, or even smaller, depending upon what is the kind of inductance I am having, inductance value I am having, what is the kind of resistance value I'm having. Depending upon that, I can have milliseconds or microseconds. So that is going to be the time duration that is needed for the response of the current control loop. Whereas here, what I have is the moment of inertia of the mechanical system. So the response time here could be of the order of seconds or even sometimes tens of seconds. So generally, speed control loop is going to take a while before it responds, whereas current control loop will respond within the order of millisecond. So the current control loop may be executed. That particular thing may be done 10 times or 20 times before one speed control loop execution takes place. So the inner loop generally is executed multiple times before the speed control loop is executed even once, or, just once before it is executed 20 times or 10 times, the current control loop may be executed. This is the kind of order of time constant we are going to have for the system. So if I try to look at, for example, DC motor drive, I am going to have the armature time constant to be only of the order of a few milliseconds. Compared to that, the field time constant is going to be larger because the field inductance is much larger. So you can have tens of millisecond or hundreds of millisecond as far as the field time constant is concerned. Compared to that, the mechanical time constant is going to be at least a few seconds. Okay. Compared to all this, the thermal time constant, if I am talking about the thermal time constant, that is going to be much, much higher. This may be of the order of minutes or, hours also sometimes. So these are the different time constants normally involved in a drive system. So we will continue with the control of electric drives and sensing in electric drives in the next class.